So hello guys, I have to do this video to put it out there for majority of us to take advantage. Okay, so I wanted to go through it. I'll be breaking it down step by step, how to derive the cost minimization. All right, you have to know that M here is the total cost, which is the sum of the expenditure on labor and capital. Is that okay? Which here is a function of labor and capital, right? So in deriving this, we have to introduce the Lagrangian multiplier such that we have Z to be equal to WL plus RK. Now, there is something you need to know. Most of us are used to, okay, when we are talking about cost minimization, then we have to use minus. While maximization, we have to use plus. But there's something I discovered. Whether you use minus or you use plus, you are still going to arrive at the same thing. All right. So since we're all already used to using minus for minimization, I'm going to use plus. We introduce our lambda into brackets. We have this now. This we have to move. Is that okay? Q, take away the function of L, comma K, close the bracket. And the next thing we have to do is to use this lambda to open this. So we have WL plus RK and plus Q lambda, because lambda times this will multiply. Then this times this you have minus F of L comma K lambda. All right, so it is at this point now we'll have to now differentiate. So we differentiate our Z with respect to labor and capital. All right, so we are first and foremost going to differentiate labor. That is to differentiate Z with respect to labor. We're going to have to differentiate this. You have W left. Then this will be 0, this will be 0. Then you have minus derivative of this, K, lambda, all over the L. Now, there is a way you can also differentiate this such that this will go, then you are left with this and this. That can be done. Then this also can be done. Now, everything equals 0, don't forget. If that is done, we are going to have W equal to F of L, K, lambda, all over the L. This can name this, let's name this as equation 1, equation 2, and this will be equation 3. These are we following. Now that we've gotten this, we now have to find the derivative of Z with respect to K. All right, so we're going to have to differentiate Z with respect to K. We'll have, this is 0 automatically, so we have R, then this is 0 2, then minus, find this, which is F, then label slash capital, lambda, then divide by your capital, equal to 0. So this becomes finally R equal to, then you have your label slash your capital, lambda, equals to, this is equation 4. All right. Now, once you know this, then you don't have a problem. The next, you're going to combine both equation. You're going to combine both equation 3 and 4. That is divide equation 3 by equation 4. And what is our equation 3? This, which is W equal to, change, have this, lambda all over, then divided by, which is, can even do it this way, equal to here, so we have W over R, is R, then divided by function of L, K, lambda all over the K. All right, now this can be simplified as W over R equals to this, lambda over the L, and divided by L comma K, lambda over the K. All right, now we can swap this, so we have L, K, this, times the K, all over change L, K, lambda. So the whole of this, we cancel this. So you are left with W over R equals to K over in F. We can now say W R is equal to marginal product of labor of capital all over marginal product of labor. And this is the same as marginal rate of substitution. Is that okay? We realize that even when we use plus, we didn't even feel it. But we got to this point and everything was okay. Is that okay? Bye.